We saw from our randomization distribution that we're not working with a bell-shaped distribution anymore. These are generally right-skewed distributions, and again, it's a family of distributions with degrees of freedom, much like what we saw with the t distribution, in a table with k cells, so that means k categories. In our example, that's the number of colors of M&Ms. We want k minus 1 degrees of freedom. So very similar to what we saw with t distributions, except it's not n minus 1. We don't take the number of M&Ms total, which was 90. We take the number of colors total, which was 6. So in our case, we had M&Ms k equals 6, so we would want a 5 degrees of freedom distribution. And there is a 5 degrees of freedom distribution drawn here, which is this one. And that does look pretty similar to the randomization distribution that we saw. So our 5 degrees of freedom. In general, these are right-skewed. And another fun fact about them is that the mean is equal to the degrees of freedom. So for example, if I take my df equals 5, and I draw a line down to 5 on the horizontal axis here, that 5 should be the mean of the distribution. We can see that illustrated here by the fact that, well, if it were the median, we would have equal areas on both sides, right? But as the mean, it's going to be just a little bit pulled right from the point at which we would have equal areas. So that means that these areas should be pretty close to equal, but the area on the right is a little bit smaller than the area on the left. And that looks to be true from this picture. So the mean of the distribution is equal to the degrees of freedom, which means that until we know how many degrees of freedom we have, looking at a chi-square statistic, we don't necessarily know off the bat whether that's a large value or not. It's all relative to how many degrees of freedom we're working with. Our chi-square statistic of 15, or 15.2, was fairly large for a 5 degrees of freedom distribution, but we can see that if we had had 15 degrees of freedom, a value of 15 is no longer really considered large. So it's all relative to the distribution we're working with, which is all determined by the degrees of freedom, which in turn is all determined by the number of categories. We're going to find these p-values using distribution theoretic methods, two ways that are very similar to one another. One of them is what we're going to be able to do on tests, which is, given a graph, let's locate our chi-square test statistic, fill in the tail, and give a very rough estimate of what we think that p-value would be. So for example, this graph here is of the correct degrees of freedom for our question. So we know that in this case it's 5 degrees of freedom. Our statistic was 15.2. That was my chi-square test statistic. And therefore my tail area is this little region over here. This does look pretty small, and I'm going to try to ignore what I already know because we've already calculated this p-value. So I want to think about it in terms of maybe just, it's easier to say yes or no than to come up with a number. Start with 10%. That's the largest significance level that we typically use. It's definitely less than 10%. Now let's go down to 5%. Does this look less than 5%? I would still be inclined to say yes. Now let's go down to 1%. Do we think it's more than or less than 1%? At that point, it might be sort of hard to answer. So maybe I'm going to say it's around 1 or 2%. Let's go ahead and just say 0.01, which is 1%. Very reasonable estimate, even though we know from our example we already did that it, at least from the randomization distribution, it came out to be less than 0.01. Let's see what it actually comes out to be in the theoretic chi-square distribution. So we're going to go to theoretical distributions, chi-square. We need to enter the correct degrees of freedom for the M&M study. We've already said a few times that's 5. And then we will find our p-value using a right tail again and using our chi-square test statistic as the boundary value. So coming back to StatKey, I want to keep this tab open. So I'm going to right-click on StatKey and select Open in a new tab and come over to Theoretical Distributions chi-square is where we're going. 5 degrees of freedom. Right tail, click on my 12.833 and enter my 15.2 or 15.202. It's hardly going to make a difference. And I get a p-value of 0.0095. So actually my estimate of 0.01 was very, very close because that 0.0095 is really close to 0.01. What we want to do to try to get practice with this method here is on your homework, especially if it's a StatKey problem, I'm sorry, not a StatKey, but a Wiley Plus question, they're going to be asking for a precise p-value. So you will have to go into StatKey and get StatKey to calculate the p-value. But what I recommend is when you first get to the graph in StatKey, after entering the degrees of freedom, but before selecting right tail, just try to locate your chi-square statistic, picture that graph, and try to estimate in your head what you think that p-value would be, and then go ahead and get StatKey to calculate it. I'm not expecting these guesses to be really accurate because it's hard to estimate area. But we do want to have some process to simulate this idea of finding a tail probability that we can do on tests when we don't have access to technology. And so what I will want is, if it's really important that I get the correct answer for whether it's less than or greater than 0.05, I'll make sure that it's really obvious, right? That maybe if it's supposed to come out greater than, it's actually 0.3 or something. And that if it's supposed to be less than, maybe it'll be well, this one here would be pretty obviously less than 0.05. But I wouldn't expect you to know whether this one was greater than or less than 0.01. That would be a really difficult judgment call to make. So do your best at estimating these and realize that you're mostly going to be graded on understanding the process, understanding what you're trying to estimate, and get something that's in the ballpark.